Let's dive into a really fascinating explainer today. We're looking at Eyeriss. This is a custom AI hardware accelerator designed by researchers at MIT, and it was built to solve one of the absolute biggest bottlenecks in deep learning. If you've ever wondered how we can actually run massive neural networks on edge devices, without draining your phone's battery in 5 minutes flat, this explainer is exactly what you need. Specifically, we're going to focus on how this chip brilliantly connects 168 individual processors to make that happen.
But before we get into the weeds of how those 168 processors talk to each other, we have to start with a surprisingly tricky question. When an AI chip processes a complex, deep convolutional neural network, what's actually draining the power? Is it the really complex math? We're talking about billions of multiply and accumulate operations here. Or is it something else entirely?
Believe it or not, it's the data movement. Moving a single piece of data from an off-chip DRAM memory costs up to 200 times more energy than just performing an operation in the chip's local memory. Basically, the math itself is super cheap, but fetching the numbers to actually do that math, that is incredibly expensive. So here is our roadmap for today. First, we'll look at the AI data bottleneck. Second, we'll meet the Eyeriss architecture. Third, connecting those 168 processing elements. Fourth, the row stationary solution. And finally, energy efficiency in action.
Section 1. The AI data bottleneck, finding the limit. Let's look at the main problem with earlier accelerator designs and why they completely hit an efficiency wall.
So previous architectures kind of had tunnel vision. Designs like weight stationary or output stationary only optimized for reusing one very specific type of data. Weight stationary focuses purely on minimizing weight read energy, while output stationary minimizes partial sum energy. The problem with that? Well, neural networks change shapes and sizes all the time. When the dimensions of a layer shift, these fixed, rigid designs suffer massive performance drops because they're entirely biased towards just one data type.
Section 2. Meet the Eyeriss architecture, a spatial approach. To solve this rigidness, the MIT engineers completely rethought the physical layout of the chip to optimize the overall system energy.
The best way to think about Eyeriss, which is designed for real-time deep learning systems, is less like a traditional computer processor and way more like an highly optimized factory floor. The entire goal of this factory is to eliminate unnecessary movement. If a worker needs a specific tool, they absolutely shouldn't have to walk all the way across the factory floor to grab it, especially if a neighbor can just hand it right to them.
So to stop workers from constantly trudging back to the main warehouse, Eyeriss introduces a 4-level memory hierarchy. It pulls data from the off-chip DRAM, stages it in a 108 kilobyte on-chip global buffer, passes it through an inter-PE network, which is the communication between the processors, and finally lands it in these tiny half-kilobyte scratch pads located right inside the individual workstations called register files.
When you look at the math, this strategy is just brilliant. Pulling a piece of data from a neighboring worker station via that inter-P network only costs about twice the baseline energy. Pulling it from the local register file, that is the baseline, just 1x. Now compare that to fetching it all the way from the DRAM warehouse at 200x. The whole system is designed to keep data as far down this hierarchy as mathematically possible.
Section 3. Connecting 168 processing elements, the spatial array. Now we zoom into the core focus of our explainer. How exactly do we wire all these factory workers together efficiently to make this local sharing happen?
This is the absolute heart of the chip, the spatial array. Eyeriss features exactly 168 processing elements, or PEs, physically arranged in a 12 by 14 rectangular grid. Because they're laid out physically like this, these PEs can pass data directly to their immediate neighbors. They exploit spatial producer-consumer relationships, completely bypassing that global buffer for their intermediate steps. Instead of relying on some clunky global cache to stage every single piece of data, Eyeriss uses a custom network on chip. Think of this as the factory's high-speed conveyor belt system. It supports multicast, meaning it can broadcast the exact same data to a bunch of PEs all at once. And it also handles point-to-point delivery, passing data between neighbors in literally a single clock cycle. Now, to manage all this data traffic without causing massive collisions on the chip, Eyeriss uses separate dedicated networks. The global input network streams specific rows of data directly to the PE array. At the exact same time, the global output network reads the finished partial sums and seamlessly routes them back to the buffer. It's really just a perfectly choreographed dance of data.
Section 4. The row stationary solution, maximizing data reuse. Okay, so we have 168 processors beautifully wired together in this grid. But what exactly is flowing across those connections to make it run so efficiently?
Well, Eyeriss relies on a very unique data flow called row stationary. Since high-dimensional 2D convolutions are massively complex, Eyeriss uses a strip mining technique. It basically breaks large chunks of data into small, sequential strips, mapping them into simple 1D primitive steps. First, a single processing element loads one row of filter weights. Second, it flows one row of input feature map pixels directly across those weights. And third, it accumulates the partial sums locally.
Picture just one of those 168 processing elements doing its thing. Say it has a 3-entry filter row applied to a 5-entry input row. The PE efficiently knocks out 9 sequential computations to produce 3 outputs. The coolest part? The filter weights stay completely stationary in the local register while the inputs just slide right across them. All of this data reuse happens using only the incredibly cheap local scratch pads.
By mapping data to these PEs in units of simple 1D rows, Eyeriss becomes the ultimate multitasker. Unlike those older, rigid architectures we looked at earlier, the row stationary method optimizes overall energy by keeping inputs, weights, and partial sums all moving efficiently, without unfairly favoring just one data type. It adapts on the fly to whatever shape the neural network layer happens to take.
Section 5. Energy efficiency in action, real-world results. Let's wrap things up by looking at the tangible results of this perfectly structured architecture. Does perfectly connecting 168 processors actually pay off?
Well, yes. But beyond just the data flow, Eyeriss is also smart enough to exploit the actual data it's processing. Here's a fun fact. Deep learning data is absolutely full of zeros. Eyeriss uses run-length compression and special data gating logic to take advantage of this. If it spots a zero coming down the pipeline, it literally gates the circuits, completely stopping the data path from switching. Doing absolutely nothing when a zero appears saves an extra 45% in processor power. That is huge.
The final result of this 168 processor network is, frankly, staggering. When you benchmark it on heavy-duty, standard networks like AlexNet, this architecture is 1.4 to 2.5 times more energy efficient than previous designs. It can process 35 frames per second on a mere 278 milliwatts of power. That, right there, is true edge computing efficiency. So, I'm going to leave you with this to ponder. As our neural networks grow ever more massive and our smart devices grow ever smaller, how will brilliantly interconnected grids of processors, just like Eyeriss, enable the future of fast, unplugged artificial intelligence? Think about it. What actually happens when every single device in your home has its own hyper-efficient factory floor built right into the silicon?